Alright, my name is Sylvia Ujwary, and I'm an undergraduate at Levy Lab at University of Pittsburgh. And today I'm going to be talking about the transport properties of BSCO on LAO heterostructures. So, as many of you probably know, LAO has quite a few interesting properties, such as superconductivity, which can be controlled by field effects. It has tunable spin-orbit coupling and electronically controlled ferromagnetism. And our lab has developed a method where we use conductive AFM to create nanowires at the LAO interface. So this is simply a diagram of how we do this. We have our LAO and our gold interface contacts connected to the interface. Then we introduce a conductive AFM tip, and if we apply a positive voltage to the tip, we find that we draw protons to the surface, which then induce these conducting sections at the interface. And if we simply apply a negative voltage, we find that we can erase any of these sections we want to. And these nanowires can be as small as 2 nanometers. So one of the motivations for this project is simply that coupling LAO with different materials can create new effects. So our lab has been working on graphene LAO samples, and they found that at LAO, the nanowires were able to gate the graphene, and it had very high mobility and gating, as you can see in this graph, just the gate voltage versus the conductance. So another motivation for this project is that layer 2 materials can allow us to study interesting phenomena. So we are interested in studying a proximity effect, and this is just an example of that with BSCO, where the Birch lab put BSCO on top of the topological insulator bismuth selenide and found that there was a proximity effect. And we are also interested in studying Coulomb drag, where a current in one material, in one 2D electron gas that's separated by another 2D electron gas by a small distance. So the current induces a drag voltage in the other material. Okay, so BSCO is a high temperature superconductor with a critical temperature of around 90 Kelvin, and the critical magnetic fields are 1 millitesla and 200 Tesla. So specifically, we are using exfoliated BSCO, which is very similar to how graphene is exfoliated using the Scotch tape method. So this is a topography image of a BSCO flake, and you can see here where we have the distance of this red line versus the height. You can see that there's very sharp boundaries at the edge of the flake. Okay, so this is what our sample looks like. We have a grid of gold electrodes, and we place wire bonds on the canvases that we're interested in. So this is simply the LAO. And we have our BSCO pieces that are randomly scattered around the surface. And this is just a zoomed in image of what you just saw, where we have electrodes at the 4 corners, and these green lines are the nanowires that are written at the LAO interface, and there are several of them simply because this sample is not very clean, and it can be difficult to write a single wire across this about a 70 micrometer length. So we simply write a couple, and that gives us good results. Okay, and here on the left, there is the BSCO in purple, and this piece of BSCO happens to be sitting on the bottom left electrode, and we found that because of this, we were able to gate the piece of BSCO. And this is just a side view of what's happening, where the nanowires go right up to the BSCO, and it's separated by the LAO layer. Okay, here is a quick movie. Yeah, so we're drawing the first electrode, and then the second set of nanowires. Okay. So you're interested in seeing the magnetic field dependence of this system, and so we swept the gate voltage from -5 volts to 15 volts, and temperature from 132 Kelvin to 70 Kelvin, and we measured conductance on the z-axis here, and repeated this for out-of-plane B fields from 0 to 5 Tesla. So this is just another view of the data, where we have temperature versus gate voltage, and then conductance on the z-axis. I guess I should still make this bigger. Yeah. Okay. Well, what you want to notice is that we see a dip around the superconducting transition temperature of the BSCO. So now we want to look at how this dip evolves as we increase the magnetic field. And come on. And the computer froze. Okay. And the computer froze for a second, so just need to get my bearings again. Okay, just okay, so we're looking at this dip, and you can see the difference between these two high conductance areas begin to decrease as we increase the magnetic field. And this is just how it looks on the waterfall plot. So you see, another interesting thing is that at 1 Tesla, we see the dip actually increase from 0 Tesla. So you see, and then you can sort of very clearly start to see it decrease through 5 Tesla. And additionally, there is this little feature happening around 3 Tesla and 4 Tesla, and we don't yet have an idea of what that is, but we notice it. Okay, just a summary of the data from 0 to 5 Tesla, and again, with the waterfall plots. Okay, so we were able to see a gating effect, and this occurred with a dip in conductance that appeared at the around the superconducting transition temperature of BSCO. And our working hypothesis is that the dip may be associated with electrons scattering off of vortices that penetrate into the LAO. Okay, so one set of samples that we are planning to create look like this, where we have 12 interface electrodes and 4 gold electrodes, gold surface electrodes that stick out at the center of the sample, and we are planning to have pieces of BSCO directly placed on the 4 center electrodes. And this will be nice because we won't have to rely on BSCO randomly scattered around anymore. We will definitely be able to do Coulomb drag experiments where we run current through the BSCO. So next we are interested in applying an in-plane magnetic field instead of an out-of-plane magnetic field to test the vortex idea. And finally, we plan to cool down to the superconducting temperature of LAO and see how the superconductors interact with each other. Okay, so we found that BSCO can be used as a gate to tune LAO nanowires, and we see this dip in conductance near the critical temperature of BSCO, and we think that maybe this is due to vortices that penetrate into the interface. And in general, this is an excellent platform for investigation of 2D materials. Thank you.